Hello class. Today we will be going over chapter 2.2, which is water. Which is about water, I should say. Now the reason that water is so important is because pretty much all of life on Earth revolves around water. While living things are carbon-based, like Earth has carbon-based life forms, pretty much everything is either made up of in some way or fueled by water. As like this thing says here, approximately 60 to 70% of the human body is made up of water. Water being molecules of 2 hydrogens and 1 oxygen. But let's go over why water is so important and how it's so versatile. So let's go over all this. First off, water polarity. One of water's most important properties is that it is composed of polar molecules. As we went over in the previous lesson, polar molecules, or polar atoms, simply means, polar molecules as it were, means that one part of the molecule has a positive charge and one part of the molecule has a negative charge. In the case of water, the end with the oxygen atoms are negative, or oxygen atom is negatively charged, and the two ends with the hydrogen atoms are positively charged. Water generates charges because oxygen is more electronegative than hydrogen, making it more likely that a shared electron would be near the oxygen nucleus than that of the hydrogen nucleus, thus generating the partially negative charge near the oxygen. As a result, water's polarity, each water molecule attracts other water molecules because of the opposite charge between the water molecules, forming hydrogen bonds. What that basically means, in essence, like we went over in the last video, last lesson, is in a water molecule, two hydrogens and 1 oxygen. The hydrogen atom or atoms of one molecule is going to be attracted to the negatively charged oxygen molecule of another. That will keep them together. It won't make them attach because they're going to attach to, but it will keep them close because of the attraction. We call a polar substance that interacts readily with or dissolves in water hydrophilic. Hydro meaning water and philic means loving. And in contrast, nonpolar molecules such as oils and fats that do not interact well with water, like vinegar and oil, salad dressing, are called hydrophobic. Hydro meaning water, phobic meaning fearing. So basically, if it dissolves in water, it's hydrophilic. If it does not dissolve in water, it kind of floats on it or sinks in it, it's hydrophobic. Water states are gas, liquid, and solid, and another reason why water is so valuable to life is because it can enter those states pretty easily in nature and in a lab. The formation of hydrogen bonds is an important quality of the liquid water that is crucial to life as we know it. As water molecules make hydrogen bonds with each other, water takes on some unique chemical characteristics compared to other liquids, and since living things have a high water content, understanding these chemical features is key to understanding life. Water's lower density in its solid form is due to the way hydrogen bonds orient as they freeze. The water molecules push further apart compared to liquid water. With most other liquids, solidification when the temperature drops includes lowering kinetic energy between molecules. Kinetic energy is applied energy. For clarification, I believe we went over that in the last video, but I don't remember. Potential energy is like something on top of my desk. On the edge of it, the closer it is to the edge, the more potential energy it has, and then once it falls off, the time it's falling off is its kinetic energy. The lower density of ice is an anomaly because it causes it to float at the surface of liquid water, and the reason it floats is because of how less dense it is compared to liquid water, such as in an iceberg or ice cubes in a glass of water, etc., etc. And here we got right here. Hydrogen bonding makes ice less dense than water. The lattice, I guess, structure of ice makes it less dense than liquid water's freely flowing molecules, enabling it to float on water. Because of the way the water molecules bend, it's kind of hard to explain. Like, this photo doesn't do a great job explaining it, but as you know, as we've gone over, it's not like it's hydrogen, oxygen, hydrogen. It bends due to oxygen being more electronegative than hydrogen. Basically, the oxygen is making the hydrogens bend to its will, if you will. So in that case, oxygen and these two bend, so there's a slight bend to it. And when these atoms right here are frozen, in other words, they are not vibrating nearly as fast as they are in liquid or gas form, this bending causes it to have a certain type of bonding that causes it to have more air in between the bonds, which causes the ice itself to be less dense than water, causing it to float. Water's high heat capacity. Water's high heat capacity is a property that hydrogen bonding among water molecules causes. Water has the highest specific heat of any liquid. We define specific heat as the amount of heat 1 gram of a substance must absorb or lose to change its temperature by 1 degree Celsius. For water, this amount is 1 calorie, which is what the calorie. By the way, I'm not a nutritionist, but I've heard that this term of calorie is not quite the same as the calorie we use, so just keep that in mind. It therefore takes water a long time to heat and a long time to cool. In fact, water's specific heat capacity is about 5 times more than that of sand. This explains why the land cools faster than the sea, due to its high heat capacity. And what that basically means is, of any liquid in existence that we know of, or at least any naturally occurring liquid, water keeps in heat the best. Water's heat of evaporation. Water also has a high heat of evaporation, the amount of energy required to change 1 gram of liquid substance to a gas. As liquid water heats up, hydrogen bonding makes it difficult to separate the liquid water molecules from each other, which is required for it to enter its gaseous phase, or, as we know, steam. As a result, water acts as a heat sink or heat reservoir and requires much more heat to boil than does a liquid such as ethanol. In other words, once you reach that boiling point, it takes water much less time to turn to gas than it does, say, alcohol. Even when below its boiling point, water's individual molecules acquire enough energy from the other water molecules such that some surface water molecules can escape and vaporize. We call this process evaporation. And you see this all the time. In fact, one part of evaporation would be like water on a sidewalk, or pretty much water on any surface with direct contact with the sun. Obviously, the sun is not burning the water at 212 degrees, but given enough time, the water molecules on the surface of that water build up enough energy to cause it to evaporate. Water's solvent properties. Since water is a polar molecule with slightly positive and slightly negative charges, ions and polar molecules can readily dissolve in it. Therefore, we refer to water as a solvent, a substance that is capable of dissolving other polar molecules and ionic compounds. And the opposite would be a solution, which would be the combination of the solvent and what's being dissolved. Like, for instance, salt is what's being dissolved, or sugar, salt is what's being dissolved. Water is the solvent, and when you place that sugar into the water, make it sugar water or salt water, that is called a solution. We refer to all of this as a sphere of hydration, or a hydration shell. 215 illustrates that. Here we go. Okay. When we add ionic compounds to water, the individual ions react to the water molecule's polar region, and their ionic bonds are disrupted in a process called dissociation. Dissociation occurs when atoms or groups of atoms break off from the molecule and form ions. Consider table salt and NaCl, sodium chloride. When we add in sodium chloride crystals to water, the molecules dissociate into sodium plus ions and negative chlorine ions, as we see here, because the chlorine atom, the negative chlorine atom, is attracted to the hydrogen atoms of the water molecules, and the positive sodium atom is attracted to the negative oxygen atoms of the water molecules. In fact, this is in essence why salt melts ice. Exact same principle, as you can see. Because when salt melts ice, because it's able to break, if you will, the molecules away from the ice cube. This is why salt makes ice melt. So anybody who lives in cold climates will no doubt have had either put salt on their asphalt, or have a snow plow come down and spread salt on your roads. I know a couple of ASM artists from Michigan who know all about this, and this is why, in case any of you are watching for any particular reason. Okay, well, how are we doing so far? Oh yeah, we're getting there. All right, here we go. Have you water's cohesive and adhesive properties? Have you ever filled a glass of water to the very top and then slowly add a few more drops before it overflows? The water forms a dome-like shape above the rim of the glass. This water can stay above the glass because of the property of cohesion. Cohesion allows for surface tension, the capacity of a substance to withstand rupturing when placed under tension or stress. Cohesion is when two atoms or two substances of the same like two of the same substances are stuck together. Like I mean, this is not quite the same, but you could think of it as sticking two pieces of bubblegum together. That causes cohesion because of the same substance. Again, it's not quite the same because cohesion is much harder to break. Basically, cohesion is when two or more, rarely there are two, but when two or more water molecules are stuck together. Surface tension is what causes that elasticity on the water surface. You've seen it before, where you place your hand in water, and when you lift it up slightly, it seems like the water kind of sticks to your finger. That's surface tension. That's cohesion and surface tension. You press down, and it seems like it's elastic, and you lift up. Cohesion is causing the water molecules to stick together. These cohesive forces are related to water's property of adhesion. Adhesion is when water sticks to a non-water surface. For instance, when a water drop sticks to your car windshield when you see it rain down, that is adhesion, causing it to stick. So in essence, this is fairly easy to remember. Cohesion is when water sticks to water. Adhesion is when water sticks to anything else. Let's see here. This attraction is sometimes stronger than water's cohesive forces, especially when the water is exposed to charged surfaces such as those on the inside of a thin glass tube known as capillary tubes. This is because the water molecules are attracted to capillaries' charged glass walls more than they are to each other, and therefore adhere to it. We call this type of adhesion capillary action, which I think will be important later on down the road in biology. Okay, why are cohesive and adhesive forces important to life? Cohesive and adhesive forces are important for transporting water from the roots of leaves and plants, and that's what we'll talk about when we get to plants. Let's see here, chapter in forever. Alright, pH, buffers, acids, and bases. We went through some of this in 2.1, but we're going to go into a little bit more of it now. Okay, the pH of a solution indicates acidity or basicity. If you guys recall from 2.1, how much of an acid is anything that either gives away hydrogen atoms, or in a solution that contains hydrogen atoms. And a base is anything that takes in hydrogen atoms, or it is in a solution that contains OH molecules. You may have used litmus or pH paper, filter paper treated with a natural water solubility dye for use as a pH indicator tests how much acid or base exists in a solution. And if any of you have taken chemistry class, it's paper that changes color when you put it into some kind of solution. Hydrogen atoms spontaneously generate pure water by the dissociation of a small percentage of water molecules into equal numbers of hydrogen ions and hydroxide ions. And we're going to get through all this because none of this is really that important. Non-neutral pH readings result from dissolving acids or bases in water. Using the negative logarithm of a generate positive integers, high concentrations of hydrogen ions yield a low pH number, whereas low levels of hydrogen ions result in a high pH level, high pH. In contrast, hydroxide ions yield a high pH number. And low amount of hydroxide ions yield a low pH number. An acid is a substance that increases hydrogen ions, like I said, and a base provides either hydroxide ions or other negatively charged ions that combine with hydrogen ions. But generally, it's going to be hydroxide ions. The stronger the acid, the more readily it donates hydrogen plus. And of course, the stronger the base, the more readily it accepts hydrogen plus. So basically, there are two ways to define bases and acids, and you go into more of this in chemistry itself, which I will gladly do if I'm done with biology and you guys want me to do chemistry. I'm not a chemist, I'm a biologist, but you have to know chemistry, even basically. But in essence, the two ways to define it, as I said earlier, just to clarify, are an acid gives hydrogen atoms, H+, and a base receives hydrogen atoms. Or, in a solution, an acid solution, a solution that's more acidic, has hydrogen atoms more saturated in it. The more saturated, the lower the pH number. And a base has a saturation of OH molecules, hydroxide molecules. The more concentrated it is, the higher the pH. So a pH of 2 will have an abundance of hydrogen atoms, H+ atoms, and a pH of 13, a solution of pH of 13 will have mostly hydroxide, OH negative atoms. And the pH scale determines all that, like I just said. And it looks like we are done. So the next time we will be joining each other, we will be going over carbon and why that is the main atom in organic chemistry and in life as general. We'll be going over why its electron shell is perfect for life, how many combinations you can have when you combine atoms, and how versatile it can be when other carbon atoms combine with it. So I just want to thank you all very much for joining me. I will see you next time, and God bless.